Hello friends, welcome to Joy of Life. So today another important topic that we are going to discuss is about quicksort. So this is one of the most commonly used sorting algorithm, and we are going to understand it in all details and explore it to the all possible extent. So here I have taken an array where we are going to perform it, and then we are also going to come up with the pseudocode as well. So before we start with the actual algorithm, I would like to tell you a few things about quicksort. So in worst case, if you notice that quicksort performs at order of n square, but this is one of the most commonly used sorting algorithm. Why so? Because generally what has been seen is that a quicksort can outperform a merge sort or a heap sort easily by many times, right? Though it's a little contradictory thing, but the worst case of quicksort is very rare. It's not going to happen so often, right? This quicksort is also known as a partition exchange sorting, right? Because what we do is we pick a pivot element and we try to put the pivot, and based on the pivot we partition the entire array, and then we try to solve the sub arrays that we have, right? So as the name suggests, like partition exchange sort, so partitioning is one of the most key element for a quicksort. And another key element is choosing the pivot. There are various methods in which you can choose the pivot. You can choose the first element as pivot, you can choose the last element as pivot, you can choose a random element as a pivot, you can choose the median as the pivot, the middle element as the pivot. There could be several ways based on your data that you have, right? So we are going to go, since our data is random over here as you see, so we are going to use the last element and we are going to implement the quick sort or the partition exchange sort, and we are also going to see in all the details first, and then we'll also look at the pseudocode and understand it in all details. So as mentioned, in the worst case scenario, which is very rare in case of a quicksort, is the complexity is order of n square. But in general cases, it's n log n. We are going to see that as well, like how we get a n log n and understand that in details. And the best part is that quicksort does not take any extra memory. It's an in-place sorting, so we don't need any extra space over here. So other than the stack space, right, that we need for the recursion, we don't need any other thing, right? So basically how it works is it goes with a divide and conquer approach. So we divide based on the pivot, and then we slowly conquer the entire array and get it sorted, right? So we are going to take this example and we are going to see how it all works, right? So let us take this array and understand it in details. So what we first do is, as I mentioned to you, that we are going to take a pivot. So let's take the pivot. As we discussed, that we'll be taking the last element as the pivot. So initially what happens is we do not have any partition, right? So we have only one partition. So I have denoted it with from left to right, which is the size of the array. And what we have done is we have picked up the last element as the pivot element. So the intention for having the pivot is after the first pass, the pivot should go to the position where it belongs. So once the pivot moves to its intended location, that means all the element before the pivot is smaller, but not necessarily in order, and all the elements after the pivot is greater than the pivot, and not necessarily that they are sorted, right? But it is greater. So when 5 is put into its rightful index, so all the element after 5 should be greater than 5, and all the elements before 5 should be less than 5, right? And how do we do that? So we have the marker for our left, right, and pivot, right? And now we are going to see how we are going to do that. So what I have done is I have taken two variables and we are going to see how we are going to use them in order to get this sorted. So to start with, we'll have a pointer j which will start from your left and it will go till your pivot -1. So this j over here is supposed to travel all the way from here till here, right? Not till 5, but till here, till this 7, this point, right? And we are also taking another pointer over here, which is your I, and what I will do is I will be at left -1. We'll see why so, but for now let's have these two pointers. And what we are going to do is, since I mentioned that we are going to iterate over here, so at every point what we are going to check is that is my element pointed by j is lesser than pivot or not. So in this case, our pivot is 5, right? So is 6 lesser than pivot? No, it is not. So what I'll do is I will increment j, right? So now is my element pointed by j less than pivot? Yes, it is less than pivot. So what we are going to do is we are going to increment I will come over here, and then I am going to swap between I and j. So the array would look something like this. The element has been swapped, right? So once again, I increment my j, so the j will come to the next pointer 1, and we are going to see that is it lesser than pivot? I see, yeah, it is lesser than pivot. So what we are going to do is basically we are going to increment I the same step, right? And we are going to swap I and j. So again, we continue to do the same thing. We increment j and we check it is smaller. Yes, it is smaller. So we first increment I and then we do a swap. So again, we increment I and this time it is not smaller. So we are going to increment it again. So j comes over here and we see that, yeah, it is smaller than pivot. And then once again, we are going to increment and this pass ends over here, right? We have no more element. J has reached to its intended destination. Now, if you just look at this array over here, what we are going to do is we know that I is the marker which is holding the element smaller than the pivot, and it is holding the right edge of it. So if I just increment I, just look at this step. If we just increment I and do a swap with my right or with my pivot, right? What will happen is we are going to take this 8 and do a swap with 5, right? So 5 will come in this position and 8 will go in this position, right? So I have changed the color of 5 to white to make sure that 5 has come to its intended place. So all the elements over here are smaller than 5. All the elements here to the right of 5 is greater than 5, right? So we have successfully established a partition over here, right? From 5, we know this is a subarray that needs to be sorted. This is a subarray that needs to be sorted, right? So now what we are going to do is we are going to spawn 2 subarrays from this position, right? One for the left part of 5, one for the right part of 5 to get that sorted, right? So far what we have done, we have just did a partition over here, right? So if I put this over here, so let's put this pseudocode of partition. So we got an array over here and we got a left and we got a right. And then the first thing that we did is to find out the pivot from it. So pivot was basically, we can say this, that the right element that we have got is my pivot. And what we did, we set a I that was pointing to left -1, right? And then we started a loop which will start from left and go till right -1. So we have seen over here that it came from till over here, right? Not the full length, and it started from the left and I was at left -1, right? And at every step what we did is, if it is smaller, what we did every time, we incremented I and then we did a swap. So I've just mentioned the function called swap over here, which will take I and j and it will swap the elements between them, right? And we are passing the array, of course, for swapping, right? And when we exit out of this loop, when we are done with this loop, what we did was basically we did a swap again, right? We did a arr with I +1 and right we swapped, right? So right was nothing but the pivot element, right? And this function should also tell me that where my pivot is, right? Because I just passed him the array and the left and right. I don't know what my pivot is, but my actual quicksort function, which will call this function, which we are going to see shortly, what we need to tell him that this is my pivot over here. So I will be returning I +1, right? That's where we have put the pivot. So this is nothing but my pivot position, right? So at the end of first pass, what we see that 5 has been in its right place. And now we are going to see how the next iterations will go. So if you look at it, what will happen is this part of the code, this will spawn a function, right? With only this subarray, and the right part will also spawn from here. So this is a tree like structure. If you see over here, so this has spawned these two functions, right? So what we are going to do is we are going to perform the same partition. So this time left is passed as this and right is passed as this, and for this array left is passed as this and right is passed as the other one, right? So this is nothing but a tree like structure, right? It's a recursion tree that's coming out. So one tree will be this one and the other tree would be this one, right? And both will have its right left, right? So how would that function look actually, the quicksort function, that actual function that we are talking about, right? Your qsort function, this will be called with your main array that you wanted to sort and your left and right. That's what we have. We didn't have anything called pivot, right? Until the left crosses the right, and every time what we are going to do is we are going to call the function over here to partition. The partition, what we are going to do, we are going to pass the array, the left and the right. So this is how it's going to look. And over here, if you remember, the partition will tell me that where should I break my next partition, right? So I will receive a variable, the return type in a variable over here, which is like my pivot, right? So pivot position that I'll be getting, right? Not the pivot number. So I'm returning the index over here. So now what I have to do from this step is I have to call this function all over again, right? Because we are branching out. So we are going to call this qsort again with the left half and the right half, right? Left partition will start from left and it will be till p minus 1, right? That's where my partition is ending. And the other function will be starting from just the next index of p, right? So it will take arr p plus 1 and right. So one element is disappearing in between. And what is that element? That element is nothing but what we have found over here. So the partition is setting the first element in its right place, right? And then we are going into this recursion, right? So first time what I get back is this index, right? So 0, 1, 2, 3, 4. So we'll get back 4 as the index. And it will spawn two trees over here, this qsort function. So one is this one, the other is this one. And we are going to do exactly the same thing that we have been doing. So first I'll go a little fast this time. So I will put it to left minus 1 and I will put j to the left and I will pick the last element as the pivot. And what we are going to do is we are going to see if it is lesser than pivot or not. So this element over here, this is lesser than pivot. So what we are going to do is we are going to increment I and then perform a swap. So nothing will happen this time. Both the elements will be pointing to the same index, right? So if we perform a swap, nothing's going to happen. The main intention is to move I forward. That is where our key lies, right? Again, I'm going to put it at j. And is it lesser than the pivot? Yes, it is lesser than the pivot. So we are going to increment and again perform a swap with the same index. So nothing's going to happen. We are going to go to 2, increment I and then perform a swap. So nothing is going to happen. So if you look at this array, what has happened is 4 is sitting in its rightful position, right? So again, we are going to increment I and then swap with the pivot, right? So nothing will happen in this pass basically. So what will happen, in this case, the pivot was already sitting in its right place, right? And then I'll go to the right tree, but in actual code, it will go to the extreme left, then come back and then go to the right because of the nature of recursion over here. So it will go left, left, left and then come back. But here for the simplicity of understanding, I'm just doing it parallelly, okay? But the concept is going to remain the same. So over here, what will happen is, again, if you see over here, the pivot is already sitting in its right place. So nothing is going to happen. So over here, it will come. It will see that it's smaller. It's going to perform a swap. You can have a check and skip the swap as well if both I and j pointing to the same index, right? So over here it will come. So there is nothing actually. That's why I deliberately created this instance, so that I just wanted to show you a pass wherein no swaps are performed, right? So over here again it will come and you can see that pivot is sitting in its right place. So we are good. So what will happen this time, instead of 4 tree, so this is one of the worst cases. What will happen is it will have only one part of the tree, right? So it will not spawn two trees, but unlike the first level. So once again, I have put the elements with white over here, and only what you can see over here is there is a left subtree over here, but no right subtree, right? And over here also there is just the left subtree and no right subtree, unlike the above where we have both the subtrees, right? And once again, we are going to put the right, left, and once again, let's start with this tree over here. So we'll have the pivot over here, and I will be at left -1. So left -1 is again over here, and J is on the left, and we will go till pivot -1 or right -1. So we are going to see, is it smaller than pivot? No, it is not. So what I'm going to do is I'm going to increment J, and we are going to see, is it smaller than the pivot? And we see, yeah, this time it is smaller than the pivot. So what we are going to do is, as usual, increment I, and then we are going to perform a swap. So we have reached the end of the array, because we cannot go till pivot or go till right. We'll be going till right -1, right? So what we'll do is we'll be incrementing this part, and what we'll be doing is we'll perform a swap with the pivot. So this 2 will come over here, and the 3 will be on the next index. So we put the 2 with the white color, and then we start with the right element over here. So pivot will be over here, J will start from the left, and I will start from the left -1 index. So since J is smaller than the pivot, what we are going to do is we are going to put it over here. So we reach the end, and once again we increment I and then perform a swap. So nothing changes over here, right? So what has happened over here, since we are setting up 7, so 7 has come to its rightful index, though it was already there. I was just showing a case wherein things might look a little different, right? So all the elements in white is in its final place, if you see in the array, right? So what will happen is a tree will be spawned again. So from this branch over here, we'll have 2 subtree with 1 element each. So that means it's already sorted, right? If there is only 1 element. So what has happened now, the current state is 1 and 3 will also get in the white color. So as you see over here, that how every time we have just partitioned and we have fixed all the elements. So 1, 2, 3, 4, 5, 6, 7, 8. So all the elements is now came to its rightful index, and we are done with this sorting, right? So what happens is over here is we are breaking the array into almost equal half, right? Almost equal half. So in the average case, that's why we say that it is log n, right? When we break it into almost equal half, and we are performing this action for n items, so it will be n log n, the complexity that we have, right? But in the worst case, as you understand, that if the array is skewed up, right, it can go up to n square. So this is not the worst case. So this, I'll say, is the average case for your quicksort, and for worst case what it will be is order of n square, but it's very unlikely that you will hit a order of n square. That's why this algorithm is very popular despite of having the worst case of n square, because you will not, even I have taken a skewed up example over here, but you have seen that it has not gone till n square, right? The number of comparisons it has made is pretty less, right? So yeah, this is one of the very important algorithm that you should know, and we have also discussed about its pseudocode over here, how it works. So this is, you can directly implement it in a code, and of course I am not putting the swap function over. It's a very simple function though. So you just put a array and take ij, and then you perform a swap basically, right? So you take a temp and you put a of I into temp, and then a of I is equals to a of j, and a of j equals to temp. So it's a very straightforward code. If you convert this into any of the language, you will get your result over here. So yeah, this is the quicksort algorithm all about. I hope you have understood the concept of how quicksort works. So yeah, do let me know if you have any doubt or any problem with the algorithm or any part of the understanding of the problem. I am more than happy to help. And yeah, that's all from this video. I'll keep it short, and I'll end it over here. So do keep safe, stay at home. The cases are still rising, at least in Bangalore. The situation is very worse. I have cases in my floor as well in the same apartment. So just be safe, stay home. As long as you're safe and you're sanitizing yourself, there is nothing to worry. So that's all from this video. I hope we get over this pandemic very soon. So yeah, that's all from this video. Do take care, and once again, bye bye.